welcome to this AOIBA sponsored talk. Today we're joined by Dr. Thomas C. Altman, PhD, with an open conversation about the science and forces that make bubbles and bubble structures. So please welcome Dr. Thomas C. Altman.
Yeah, this is going to be interesting because this is unusual. I'm going to present the way I would do it for younger people, and then perhaps with each element, uh, get more and more detail. And then if you're taking notes, which I would, if you have questions, write them down. We'll try to address them. I'm going to talk about water, cohesion and adhesion, detergent, how that affects the color, polymer, and how we make a sphere. So my presentation typically is titled "In Search of Tom Noddy's Bubble Cube," and so depending on the age group, I'll go into different details. But I start, and what I've started doing is making a bunch of bubbles. Start off with hey, how many of you kids have played with bubbles? Yes, we've all played with bubbles. Did you know that bubbles change colors? What? We did not know bubbles change colors. Have you ever seen an old bubble? And oh, my camera's not focusing anymore. Have you ever seen an old bubble? We don't know what an old bubble is. Well, when a bubble starts off, it starts off with blue and green and magenta. But when it gets old, it turns golden. That's why they call it the golden years. And the seeing a golden bubble is a real magical moment. It'll grant you wishes if your wish is to see a golden bubble. And at this point, the kids stop popping bubbles and they start watching bubbles. And so I introduce myself. I say I'm Dr. Altman. I'm a bubble scientist, and I'm a scientist and I study bubbles. And so part of studying the bubbles is watching them and watching them carefully. And so I will make a bunch of bubbles, and we will try to watch some to see if some of them turn golden. And as they're watching, I say, as the water evaporates, the bubble gets thinner, and it affects the way that light interacts with it. And so there's a golden bubble. Okay, see the golden bubble? All right, now if you watch that carefully, it'll turn clear. And once it turns clear, if you keep watching it, if it stays in the air long enough, it will start to become invisible. It turns into a ghost bubble. And then the bubble disappears. And so now the kids are watching intently, trying to find a ghost bubble and trying to see a bubble disappear, because these are not things that they've ever really paid attention to before. And if you just hold a bubble on a wand, it does not go through this process. The bubble is getting fed water from the wand itself. And so this doesn't happen with just a bubble on a wand. It only happens with bubbles as they're floating in the air. And so that's where I go. And then I tell them, as a scientist, I studied light and color. And so I always had bubbles because of the way the film of light reflects, and we're having the problem, reflects light. And it reflects the different patterns, and you can see color in it. And you got to get the lighting just right in order to see that. But if you make a bubble, then it's got a lot of different angles, and so you can see the colors with a bubble much easier. And so I always played with bubbles. And then I noticed with a thin film, if you blow into it, you can make a bubble. So isn't a bubble just a thin film? And so doesn't it make sense that I could blow into the side of that film and make another bubble inside? And then obviously this works much better with a large wand. But then you can do the bubble into the bubble. And you guys have all seen the bubble in the bubble. And that really amazes the kids. And so I tell them that that was part of my science, part of my physics. I did that for many, many years. And then I heard about this guy that made a bubble cube. And how can a bubble form a cube? Well, it can't. And so I then say, we want to figure out how a bubble works and how you can make a cube out of a bubble. And so I say, well, as scientist, I got to go back to the start. Uh, what's a bubble anyway? And so I start off, and depending on the age of the kids, I may skip part of this, but I always talk about the fact that water is incredibly unique. Water is one of the most amazing materials on the planet, and a drop of water is an incredible thing. And they've seen drops of water because it rains a lot. As a matter of fact, it's raining a lot right now. And if you have a population of kids and you're doing a workshop with this, there's a very common activity that we do in science to show that that water is so unique. And what's so unique about water is that it bonds to itself. It holds on to itself. We call it cohesion, the force of water molecules attracting other water molecules. It actually pulls itself. And if given opportunity, water molecules will pull together and form a perfect sphere. And I have a picture. I don't want to try to find it right now and share my screen because I've got this working and I don't want to mess with anything. But there's a number of pictures of a water globe in the International Space Station, and it's a perfect sphere. And it looks like it's made out of chrome or something. It's just amazing. But on Earth, you can see this. On Earth, we have gravity. And so if you put a couple of drops on water, they form a dome. I don't know if my camera will focus in on it, but there's an activity you do with kids. You get little cheap little plastic eyedroppers and some coins, and you count to see how many drops of water you can put on a penny. The coin has a little ridge to it, which kind of helps, but you can see that, and I don't want to spill it at this point. But what's happening here is that the water molecules are pulling in on itself. Cohesion is the name we give that process. And with little kids, I tell them cohesive from or co-workers or people in a group. The cohesion in a group is holding together. So this is a cohesive force. Water pulls inwards on itself. And so it loves pulling in on itself. Now at the surface, we've got a little weird thing that happens because the water molecules are pulling in all directions, up and down, left and right. But at the surface, there are no water molecules above it. So it doesn't pull up. It just pulls side to side and downwards. And it pulls side to side and downwards with a little bit stronger force than in the middle of the fluid because it has the upward direction it can pull in. And so at the surface, it's a little bit stronger. And we have a name for that. We call it surface tension. And it's produced by the cohesive force of water at the surface. And so we oftentimes just generalize the bubble and the water droplet. We just talk about surface tension. But that's the result of cohesion, which holds all of the water together to a drop. And so we put that there. And now we have water. Water has this cohesive force. It wants to stick to itself, and that produces drops. Now, water has another amazing force, and that's called adhesion. Water likes to stick to other things, and so if we've got a wand or something like that, we put it into water. We can get water to stick to it. And you can see the water sticking to it. And water makes things wet. And that's probably not a new concept, but it is the one that we're interested in. Water makes things wet. Oh, that's great. But now, how do I go from water cohesively holding itself together and adhesively sticking to things? How do I turn that into a film? How do I, because I already showed them, you can make a film of soap, a soap bubble. Somehow soap plays a role in this whole thing. And I got to get a film here. There we go. Oh, it'll work. it worked before. Oh yeah, it's just so thin I can't see it. So how do I get that to form a film? And the process involves adding a detergent. And you add a detergent. And for kids, I really don't talk too much about um, uh, the different characteristics of the detergent molecule. With older kids, I would. But essentially, what happens is when you add soap to the water, it weakens the surface tension, makes the surface tension a little bit weaker. In this scenario, gravity is trying to pull it flat, and the cohesive force, the force of the water pulling in on itself, pulls it back together. And so it forms a drop. If I add a little bit of soap to it, and or I just take soapy water, is this soapy water? And I try to duplicate this with soapy water, I cannot get the dome to form as tall because gravity is now strong enough to overcome the reduced surface tension. The cohesion of the surface is weakened by the soap. Now, what's happening is the soap molecules, the hydrophilic ends of the soap molecules, are actually getting in between some of the molecules of soap, of water, and it weakens that attractive force. And so the surface becomes weaker, and it actually reduces the surface tension. And so what happens now is that when I put a wand in there, I can get the water to attract to the is that a film? Yeah, it is. Okay. I can get the water to attract to the wand by adhesion and attract to itself by cohesion. But because I've reduced the surface tension, I can cause the water to stretch out into a film. The force pulling it towards the wand or the frame is balancing by the cohesive force of the water wanting to go back to a drop, and that produces a film. And so those are the factors that cause a film to form. All right, now at this point, I would, if there are questions about that process or about that thing, I would like to address it. Damien, are you still there? Damien, could you
Yeah,
reduce me?
I'm still here. Does anybody have any questions?
About those factors, about the cohesive force of water, the adhesive force of water, or the role that detergent plays in the formation of films.
Okay, Holly Sprake Hill, uh, hydrophilic. Say that again, please.
Okay, the soap molecule itself, which uh, there's lots written about this, so I didn't really want to talk about it, nor do I talk about it very much. But the soap molecule itself, one end of it is attracted to water, and the other end of it is not. It's and so the part that's attracted to water uh, gets into it, but the other part is kind of repelled, hydrophobic, and it kind of sticks out. So on the film, it appears as though there's a layer of water, a layer of soap molecules above and below it, and so that's what causes the film. There's lots of pictures of that process. I think I covered it in my book as well. Um, Incidentally, the forces in the whole conversation has to do with understanding what's going on. The forces that we're talking about are all the same kind of force. They're electric forces. The force of attraction between uh, electrons and protons in the atom. It's similar to magnetism, and magnetism is easier to illustrate. Here's a pair of magnets, and they're floating. And so if we took the top off, which I may have this one glued to keep kids from doing just this, and to flip it over, they would attract, and here they're repelling. The bottom line is, we don't really know what's happening here. We have names for it, magnetic repulsion. We can manipulate it. We can do a lot of things. Different materials repel, different materials attract. There's a lot we do know, but the fundamental force itself, we simply call it a fundamental force of nature. It just is. It exists. A similar type of relationship exists in electricity, attraction between what we call a positive and a negative, just to differentiate them. And so we have negatives, which are electrons. We have positives, which are protons. And there's a force of attraction between them and force of repulsion between negatives. Static electricity would be the ideal example. I'm going to be doing that tomorrow, actually. And so if you build up a static charge, they repel. Brushing your hair on a cold day and the hair starts to repel. I remember people talking about that. And then your socks sticking to your clothes after they come out of the dryer, the force of attraction. And so all of these forces in water are electric in nature. And so the ultimate force is this electric force that we're not 100%, it's a fundamental force of nature. And so linked are electricity and magnetism that we just call it electromagnetic energy. And it's a fundamental force. In chemistry, there's rules that govern how things come together and how things go apart. And so in chemistry, there's the detergent molecule, and part of it is electrically attracted to water and repelled by water. And so the part that's attracted to water, we call the hydrophilic end, and the part that's repelled from water, we call the hydrophobic end. And so this would be more of a high school discussion than it would be for kids. But simply stated, the water can change its surface tension by adding the detergent to it. So it's not held together quite as strongly as it used to be. And so now instead of a ball, I can stretch it into a film. All right, does that answer that? Are there other questions?
Caroline and Cheryl, what is absolutely simplest way of describing surface tension for little children while still being true?
There's a force of attraction, Tom Noddy's going to chuckle, where water wants to be held together. Water wants to be held together. And at the top, the molecules feel a stronger attraction to the water than they do anything else. And so at the surface, there's nothing above them to be attracted to. And so they're attracted sideways with a little bit more force. And because this attraction sideways is a pulling force, we would call it tension. A pulling force is a tension force. So if you look at a tiny little piece of the surface of or if you just look at a film, it would look kind of like this. Different process entirely, but kind of like that. So for small children, you can use the example of a balloon. That at the surface, it's a little bit stronger. It breaks down immediately as soon as you start actually playing with balloons. But there's a force kind of like that that holds it together. I don't really talk about the surface tension so much with very small children. I talk about there's a force pulling it towards the rim, the wand, and I use the vocabulary adhesion, and then there's a force wanting it to be a ball, a sphere, and that's cohesion. And I also use that vocabulary term. And the soap allows the cohesive force to weaken so that we can stretch it and form the film. And so I don't always talk about surface tension. I talk about cohesion and adhesion. Surface tension is a word we use in one specific situation, and it's really the cohesive force that's causing the film.
So Ian Russell's just put a note in that says water pulls itself together.
Yes, yes. And again, water pulls itself together. Water likes to be together. If you're going to personify it, there's a force that causes water to pull itself together. And the soap weakens that a little bit so I can stretch it out. Any other questions?
No other questions at the moment.
Okay. All right. So the next thing is, how am I going to make a bubble? And that gets into another thing, because now I want to stretch this film. And naturally, you can make a bubble with soap and water. You can, with just soap and water, you can make a bubble. And so that's possible. But if I want to make a lot of bubbles, or if I want to make a big bubble, I have to add an ingredient to the water. And in one of the activities that I do, the participants actually make their own bubble juice. I use a simple GAR mix. And so I have to talk about the addition of a polymer and explain what a polymer does. And I've got this illustration that works fairly well. I've done a lot of research and I can't find anything that talks about what the polymer actually does to the water. That allows, I mean, we all know what it does. I just can't find anything that explains why. And I'm really big on why. So this illustration works. This is a plastic spring, a plastic slinky, and it's a solid. And a polymer, by definition, is more than one mer. A mer is a molecular structure, and a polymer is a bunch of these connected together. And so that's what a polymer is. And so you put polymer in water, and it begins to incorporate the water into its structure. And so it goes from being a solid that's relatively firm to a solid that's relatively flexible. And you can have longer chains and shorter chains, but the polymers, this is not a bad illustration of a polymer. And if you imagine water incorporated into the individual components, now it's part of the water and it makes the water stretchier. And so that's what I do. And as we know, when we're mixing polymers, and I explain this to the people, if you just toss this in, it'll form a clump, and some of it will become hydrated. Some of it will incorporate water. And with older groups, I would use the term hydrated. But some of it will be trapped in the middle and just form clumps. And so I explained to them that we put it in alcohol to slurry it, which separates the individual pieces of the polymer. And then we put that in the water. It can hydrate without forming clumps. I also explained that it works better after a day. And that's because it needs more time in order to hydrate to its complete length. And so I then introduced the concept of hydration of polymer, including the polymer into the mix. And now I have a film that I can stretch. And what I'm going to stretch it with is air pressure. And so if I blow on it, I should probably get a film. I can stretch it. Now, the force of adhesion, the attraction of the water towards the wand, pulls it back in. So the air is pushing against it, stretching it outwards. The adhesion is pulling it back in. But if I get to a certain length, it gets out far enough that the cohesive force of the film, the water wanting to be attracted to itself, is greater than the adhesion to the wand. And in fact, a bubble will close off. And I don't tell them the term necking, and certainly none of the math involved. But I simply say, if you blow hard enough, you can get a bubble to form. And once a bubble forms, it's a much trickier thing. Because now, and again, I'm holding this on a wand. I would do this with a free floating bubble. Well, no, I would hold it on a wand, which changes things slightly. But now I have obviously the force of gravity pulling it downwards, but I have the cohesive force, the water wanting to be back to a drop. And now it's filled with air. And so it can't because there's air in there. And the bubble tries to, it squeezes down tighter on it, but there's air in the way, and it can't, the air's got nowhere to go. And so it forms a ball. And the idea is that air pressure works in all directions for elevations close to the earth. it works in all directions equally. So there's something pushing in all directions equally, trying to keep this thing from going back to a drop. And because they're going in all directions equally, the structure that will be formed is a sphere. Now, coincidentally, that's a minimal surface. Coincidentally, well, if you define a minimal surface as the lowest energy condition for with these parameters, then in fact, no, I don't use minimal surface. I talk about the force trying to get it to go back to a drop, and the force of the air being in the way, pushing back on it. And when those forces are in balance or equilibrium, then it forms the shape that it is. And if it's just a bubble all by itself, that shape will be a sphere. And I can illustrate that by popping the bubble, and it goes back to being a film. And if given opportunity, it would go back to being a drop. So the idea that the bubble forms a sphere because it's a balance between the air inside and the cohesive force of the water explains why bubbles form spheres. All right, any questions to this point? Any comments?
Nothing's come in yet.
I'll give them a second. I'll take a quick beverage break.
Okay, hold on.
All right.
Somebody's typing.
Okay.
Okay, Caroline and Cheryl, can you make a similar simple statement for a bubble film?
I thought about this. I hate the balloon because yes, a balloon. Assuming, of course, it's a round balloon. Shaped balloons and the part where the nipple is and all those things change the dynamics of the structure. But for the majority of a balloon, the forces trying to pull it back in are relatively equal. And the air pushing back out keeps it inflated in that shape. It's hard to find a spherical balloon because of the dynamics of its construction. But yeah, a balloon would be a corollary. It'd be an illustration. Yes, I would not have a problem with that technically.
What about a flat bubble film?
Well, a flat bubble film was simply the balance. Yeah, the trampoline, and I do the trampoline bit with larger wands. The forces of attraction to the outside are like the springs on a trampoline. There's no there's it's on a trampoline. The springs provide all of the force. The surface itself doesn't have a impetus to get smaller. I guess a piece of see a rubber, if there was rubber over it, if there's anything like that, it would come in a little bit, but it would be a clump. And the water really wants to go back to being a drop. So the film, the balance between the adhesive force of the adhesion to the wand and the cohesion of the water, the soap allowing it to be thin, those forces in balance produce the film. I can't think of another analogy that doesn't involve, stretching a balloon over it has the same problems with the balloon example. But I guess if you're going to go with a balloon example for a bubble, then you could use a rubber balloon stretched around, say, an embroidery hoop that acts as a trampoline or a tambourine or something like that, where you've got a material that wants to be pulled inwards and another structure that's holding it outwards, and the balance of those produces the flat surface. So I guess that would work.
Ian Russell has a suggestion of could you hold up a piece of balloon rubber and stretch it?
Well, I couldn't because I don't have one prepared, but yes, yes, exactly. That would that would be good. That would be good enough if the kids are small. I've got it going back to a drop is one of my recurring themes, and the balloon would not obviously go back to a drop, but it would go back to its uninflated state. So I guess you could make that analogy, certainly.
Okay. Michelle, why do you not like to use the term minimal surface?
It's a description of the bubble. It's not an explanation of the bubble. I use this at Bubble Fest. Describing a sphere as a minimal surface is like saying it's a sphere because it's a sphere. Minimal surface means a sphere in this case. With these parameters, a minimal surface is a sphere. It describes it. Um, Plus, minimal surface is a really complex mathematical process. Analytical geometry, some differential calculus involved. The equations for minimal surface are very sophisticated. And I don't think people, bubblers that I've talked to, really understand how complex that is. Uh, the idea that it's a balance of forces, people can understand. Even little kids understand you push one way, you push the other way, they balance. Um, and But minimal surface is a very sophisticated term. I'm going to do the same thing with wave interference. It's a very sophisticated process, and there's a difference between knowing what something is and knowing what the word is. And often, too often, I find people throw the word out without really understanding what it is. So minimal surface is not the right word to describe why a bubble makes a sphere. It's a bubble makes a sphere, and it is coincidentally a minimal surface, but it's the equilibrium of forces that produces that. And so that's kind of why I don't like minimal surface, because it doesn't tell you enough. And the real reason is easier to understand than minimal surface mathematics. And so that's why I just a thing. Tom and I had this conversation at Bubble Fest, and I don't think I convinced him. I think he probably will still use minimal surface, but he'll at least understand the term better than before. I don't know if I won him over, but he still says bubbles do this because they want to. So
He's laughing away.
okay,
Uh,
all
I
right.
think it's on the same topic. This is from Agnes. She says, I say the bubble is round because with the attraction of soap and water, it is the simplest form of nature.
No, that's not true. Flat would be the simplest form. The round, we have to now put it in what's called dynamic equilibrium. There's actually air that's moving, that's pushing on this thing. And it's the balance of that air pressure acting on the water, the cohesive force of the water. The role of the soap is simply to allow it to stretch. And then the polymer comes into to play in that. Um, it's not it's not the lowest energy state. It's the lowest energy state under those conditions. The lowest energy state is eventually going to be the drop that it goes back to. So if we're going to be technical, and as long as we're talking science, we might as well. Um, I think that would be, how could I do that? The sphere is the perfect shape when all of the forces are balanced, and things like to be in balance. But um, until gravity takes over, and he always wins. And so I don't know if that helps, but um, um, I would say it's the shape when everything is balanced is the sphere. Does that help? Maybe.
Uh, I've just, Agnes, thumbs up? Or was that helpful, Agnes? Yes, yes, that was helpful. I'm just
Uh,
translating another question for you.
hey,
Um, So my Google Translate is doing overtime. So Sebastian, the bubble is round because of this pressure.
The bubble is pulling in and it squeezes the air. When it squeezes it to a certain point, the forces balance. And so it's the balance between the air that's in there, and air has got mass, it takes up space, it's a gas, and so it's a highly energetic material. And so the cohesion pulls it inwards, and it resists that. And that resistive force, if you're going to say action reaction, the cohesion is the action force and the pressure is the reaction force, if you're going to isolate them more specifically. Um, and uh, and so it would be the balance of those forces. Does that answer the question? I forgot what.
Uh, a follow-up from Sebastian, and the bigger it is, the less pressure there is inside.
Yeah, that has to do with mathematics, which I was going to cover a little bit later. But yes, the pressure is equal to 4 times the coefficient of surface tension divided by the radius. And so as the radius gets bigger, the pressure decreases. Now that'll shut them up.
Is that okay, Sebastian? Yeah.
Math? I didn't know there was going to be math involved. I
Uh,
thought these were bubbles.
from Andy Bubble. When introducing surface tension, I often use powder on the surface of water and then add a drop of soapy water to break the surface tension while explaining to the audience. But the fascinating part is that even after the surface tension on the water is broken by the bubble solution, the bubble still forms a round shape due to surface tension. Is this because the surface tension is still present, but just reduced?
Exactly. Exactly. It doesn't eliminate, it just weakens it and allows you to form the film instead of the drop.
Is that okay, Andy? Yeah. Okay. Uh, Caroline and Cheryl, does that apply to planets too?
Are that planets round because of surface tension?
Uh, Let me just, because I think I'm just going to ask them to,
Well,
uh,
I think planets are round because of gravity. Gravity pulls towards the center of a mass and it forms round objects. Um, uh, Gravity makes balls,
uh,
which
is
is
that
funny.
helpful?
Gravity.
Caroline, Cheryl, was that helpful?
All right.
No answer.
Okay.
I've got a couple more. I'm just translating. Um, so this one from done that one. Tom Noddy, I like that you return continually to the desire of the fluid to become a single drop. When I tell it, I add to that it really wants to be a spherical drop.
Because you personify it, because that's where it feels most at peace.
Ian Russell, sometimes it's more useful to encourage thoughtful observation than to muddle their heads with words.
Yes. That's why I try to not to use words, technical terms like surface tension or minimal surface. I simply explain there are forces at play. And I then will, as we start heading towards the cube, I try to get them to what must be happening here type of thing, figure out what's happening here. But the cohesion of water they can discover if they play with drops. So they can say, oh, there's something that's pulling it in. They might not know the vocabulary, but they know that water tends to pull it in. If you stick something in water, it gets wet. They can see that without knowing adhesion. So yeah, not knowing the words, um, because I'm a science teacher working in schools, and I recognize the fact that they're going to be evaluated by some system that is based entirely on vocabulary. I cover it, but I do emphasize the idea that these things happen whether we give them names or not. And so I agree with you, Ian. Let them figure it out for themselves. And the beauty of soap and water is that there's nothing they can do wrong. You know, if they drink it, all right, they'll learn their lesson without hurting themselves. You can just let them play with soap and water and throw in a little bit of polymer and let them experiment. I created a lab where they got water, they got soap, they got a polymer, and they had to figure it all out themselves. And what if they do it wrong? It doesn't matter if they do it wrong. The worst they're going to do is get clean. And so I love this medium for experimentation.
Okay, I'm going to pop back to Cheryl and Caroline because I'm not quite sure I phrased their question correctly. So I'm going to invite them to ask the question directly. Cheryl and Caroline?
Thanks, Damien. It's can we is using a planet as an example of a spherical shape being produced by forces pulling inwards, is that a valid parallel with a bubble producing a sphere?
Yes. Yes. Uh, the gravity pulling inwards, the builds up the pressure inside, which resists gravity, and the bubble being pulled inward by cohesion, and it compresses the air, which then resists it with air pressure. Yeah, but yeah, sure, why not?
I'm not convinced, Thomas.
I don't know why you would. That's an
Because
unnecessary jump.
they can see the moon. They can see the moon. They know what the moon looks like.
But it's not a bubble.
It's not a bubble. It is spherical.
Okay, but then you could take anything, a billiard ball, anything that's spherical, and use that as an analogy. But
billiard ball is man-made. Planets have.
well, but you just made that bubble too, so it's man-made or woman-made in this case. I understand what you're saying, and I don't.
That the ball is manufactured, the bubble happens.
All right, well then, okay, it's a natural phenomena, the shape, and if you were to say that a planet is a sphere because that's the balance between gravity pulling inward and the material pushing back out, then that would be a great analogy. It's spherical because that's the when things are in balance, that was the shape that does it.
Yes,
Great. All right.
Thank you.
All right.
Thank you very much.
All right.
No more questions.
Okay. All right. Now, the idea that as a bubble forms, the pressure inside, obviously, the perfect example of that is Tom's volcano. When you allow a path, then the air escapes. And so as I'm doing my presentation and talking the sciencey things, I illustrate all these things. And you've seen volcanoes before. Also, this one works better for holding a bubble. Why do you suppose that is? And this is one of those things where if they come up with, well, there's more surface area, and so there's a stronger adhesive force. The other thing that you introduce when you start to putting bubbles, and as part of my presentation, I tell them that the discovery of making bubbles with a straw was a game changer because it's an opening. My camera, you can focus. It's an opening, a film can form across it. I can blow on it, and I can get a bubble to form. But the beauty of the straw is I can put the bubble where I want it. So I can put a bubble here, and I can look at what's happening. And I can see that gravity is pulling the water down to the bottom, and it's going to try to form a drop. And so a lot of characteristics are happening. But watch what happens. I can put another bubble right where that drop is. And now something amazing happens. Where the two bubbles come together, you'll notice it's a flat surface. I've got a bubble, two bubbles, but between them I have a flat surface. And this is where things get exciting because I tell the kids with a flat surface, what do I need to make a cube? Again, my theme is I'm getting to a cube. Well, I need 6 flat surfaces surrounding a bubble. So now I've got a couple of flat surfaces. And then as part of my show, I then do some of the tricks that you can do with 2 bubbles, the carousel, and some of those. And I do it in such a way I act like I'm sorry. Oh, wait, let me show you. Let me show you what you can do. This is interesting. You'll love this. And then you build the carousel, or you do whatever tricks you're doing. And so that's how I incorporate the science into a bubble show, is I do the same tricks that Tom taught us all those many years ago. And then I do the dragon's egg, which is a real fan favorite. So you get the bubble to form, you do the bubbles around it. Then you let the air out of the center one, and it coalesces into a cluster of bubbles. And then you put it in the kid's hand and tell them if they keep it for 24 hours, it'll hatch into a dragon. And they all line up to get those. And that's where I make my money, because I charge 25 cents a piece for dragon's eggs. See, this is the problem. I can't hear you guys all laughing right now. Sorry. All right, so once I get to 2 flat surfaces, then it's just a matter of building from there to get to the cube. And then the idea that I can put a straw inside of that, I tell them if it's wet, then the water that's attracted to each other is just, it sees the straw as essentially part of the water. And so it doesn't pop. It doesn't interrupt the surface of the bubble. And so by incorporating a wet object into it, I can put it into there, and I can do tricks that way. I pull the drop off the bottom by adhesion. I touch the straw there, and when I pull it off real quickly, I can pull the drop with it because the water wants to stick to the straw. And so I get to the bubble being a cube. And they love that bit. Throw a little bit of smoke in there if the event. And then you can flip it off, and now you've got a bubble cube floating in air. And that was the goal of the whole thing, was to get a bubble cube floating in air. The science, not as much as the performance aspect of it. I'm using the cohesion and adhesion that I've talked about, and I'm using that to do the tricks. And so I make that the jump is part of my show. Questions before I get into the colors of bowls?
No questions yet.
Okay. Now, when I talk about the colors of a film, the colors of a bubble, I talk very carefully, and I talk about when light hits. My film has got 2 sides to it. Is there a film there? Nope. My lighting is what's throwing me off. Still don't have a film. Tom, what am I doing wrong? I got these other things in there. I'll take them out. There we go. All right. So I've got 2 surfaces, one surface and the other surface. When light hits it, it reflects. And when light hits any boundary, when light hits most boundaries, it will hit and reflect. And then light passes through because it's clear, and it hits the bottom surface, and it also reflects. And so I've got 2 rays of light reflecting, and those rays of light interact. And after a lot of research, Tom, interference is not an inappropriate word. They interfere, and what they do is they enhance one color. How that happens involves a bit of mathematics and a bit of understanding of constructive and destructive interference. To say the light waves interact and it produces the colors. And the color it produces depends on how thick the film is. That's as far into the math as I go shy of high school level. At high school level, I'll draw it and we'll do the math of showing how thickness relates to constructive wave frequency, color. But for kids, I simply say the light interacts to produce the colors. And I let it go with that. And as the film changes, as it gets thinner, the colors change. And then it brings me a full circle back to my golden bubble, that as the bubble ages, it's getting thinner, the water's evaporating, and it changes color. And then, so that kind of wraps up, what can I say? Air pressure, talk about that. The two bubble wall. Polymer, either interference is a valid term, but it's a complex word. It carries with it a lot of mathematics. Interacts is a simpler term to explain the same thing without having to introduce, well, what do you mean interfere? How does it interfere? I don't know. It interacts. How's that? Well, that's complicated. You have to go look that. I got some math if anybody needs it. All right. What have I left out? What have I left out? Any questions?
No questions on color.
Really? All right. I also do a bit on solid liquid gas in the New York State school system where I would teach and go to elementary schools. That would be a big topic: solids, liquids, and gases. And so water played a big role, and soap bubbles played into that because and it helps understanding the structure of the atom. When the hydrogen atom and the oxygen atom combine to form water, it does so in a special geometric pattern. And so when they slow down, they combine based on that pattern, and it produces crystals. Here we get a lot of them called snowflakes. And they're crystals of water. As a matter of fact, all solids, when they, great, well, my autofocus is never going to work on this thing. Well, this is just a geode with some crystals in it. So in quartz, cools from a magma, crystals can form. It's a natural phenomenon that they would form. And so that would be a solid. We'll call it a crystalline solid, and that's the definition of a solid. If you heat it, the molecules move faster, and then they separate from those crystal bonds to form a liquid. The liquid is still held together by bonds. In water, that brings us right back to coherence. And if we continue to heat it, we eventually have to break those bonds. In the case of water, that's a lot of energy, kind of uniquely so for water. It holds a lot of energy in the liquid state, and you have to add a lot of energy to get the liquid bonds broken. So now the molecules can go flying around in a gas. And so once again, water plays a big role. That's why water is used in a lot of coolants. You add antifreeze to the water to keep the water from freezing, but it's the water that carries the heat with it because this coherent, this molecular force between water molecules is so strong that you can add a lot of energy to it before it vaporizes. And so I would build a lecture around solid liquids and gases, and bubbles would play the liquid and subsequent gas part of that lecture. And that was pretty popular. You bring in a bunch of crystals, they play with crystals, and then you do some bubbles. And they love that bit. And so that's just another aspect of the bubbles as they play into science. All right. That's all I've prepared.
I've got a comment from Ian Russell on color.
Okay.
Ian Russell says it's easier just to say the color depends on the thickness.
Good point. Good point. The color is an indication of the thickness. It depends on the thickness. Yeah, that's again, my background is teaching physics and teaching the wave interference concept with all of its mathematics. And so I'm simplifying what I would do. But if I was starting fresh, I would say the color depends on the thickness. And as it gets thinner, it goes to the gold. Um, Again, I don't know what level you want to, if you're dealing with older kids, then though I don't know in your school system when they would learn the physics of that. Well, good. Yes. Color depends on thickness. Absolutely.
Question from Stephen. Do you talk about the air quality during a show?
No. If the bubbles are popping while I'm trying to do something, I will talk about, you talk about wet objects won't pop a bubble because water sees the water and it just thinks it's more water. And if water sees something that's dry, it will interrupt the cohesive force. It'll interrupt the surface as it tries to adhere to that thing, and that interruption will cause the bubble to pop. And so if because I talked about with the straw, put in a wet straw, it just sees it as more water, and it doesn't have a problem. If I was having a difficulty with a lot of my bubbles popping, I might mention that things that pop bubble are dry and the air is filled with a bunch of dry stuff, and it's dry air to begin with. But no, I wouldn't bring that up as part of my discussion unless it became absolutely necessary. It's just too many variables, too many things. It's like it is to Ian's point. Just let them enjoy it and experience it, and as from the science, have a little bit better understanding of what's happening. But you don't have to give them every single eventuality.
So from Caroline and Cheryl, how could you use an air bubble versus a soap bubble?
Like an air bubble in water.
Not sure of the context. I'm going to ask them to unmute to put their question into a context.
Thank you. The thinking of Dory, using Dory in a show, and now Dory blows bubbles underwater. Are those bubbles just as, I mean, this is water, this is a spherical shape underwater. Is there a conversation there, or just let it go?
Let it go. The water is displacing air. It's feeling pressures as the air bubble rises because of the different density. It's not a sphere. It actually will flatten as it goes up and encounters the resistance of the water. And it's the discussion has to do with liquids and gases, but it's not. Yeah, I would not.
Okay.
In the study of foam and fluid dynamics, air bubbles in water is really the big thing because there's all sorts of things that go in water that produce air bubbles, propellers, most specifically, cavitation behind things. And so that's a really important concept. And the flow of fluids is a big concept in industry and the movement of foam and things like that. But so there's a lot of research, but I would clearly not use that as an example.
Okay, what about the space bubble, the spherical water bubble in
Well,
space?
the idea that the cohesion wants to pull it back into a sphere, and without the influence of gravity, it'll form a perfect sphere. And so here, I wonder if I can share my screen. Can I do that? There's oh man, I didn't mean to open that app. Yeah, it'll get me there. The idea that water is coherent, experiences a coherent force, and apart from gravity will form a sphere is really big. This is on the International Space Station. This is a ball of water that has been left. There's no air currents affecting it. It's just sitting there, and it is spectacular. And so that's the surface of a water drop. Interestingly enough, that's one of the applications of industry in space is that you create perfect spheres. And so if you could do that with metal, you could create perfect ball bearings, which theoretically would be frictionless. And that would be a cool thing to have if you were into ball bearings. Let me see if I can close that without, okay. There's here's the interference imagery that was open with photos. There we go. So let's make this bigger for some reason. So when the light comes in, they reflect off both surfaces, and using a mathematical process, they can interfere to enhance one color over another, and that enhancement depends on the thickness. We'll just go through some of the other stuff. There's another example of that without any of the math. Here are soap molecules, detergent molecules, and water molecules. The hydrophilic ends sticking in the water, the hydrophobic ends sticking outside of the water. This is just how soap works to attract germs or to clean up dirt. The hydrophobic ends are actually attracted to oils and will surround an oil, and then you will rinse the soap away and carry with it the dirt and germs. This is a sketch from somebody's paper. The surface tension in water is pulling basically outwards, but because it's curved, you'd have to do a lot of little vector tricks. But these forces outwards resolve into an inward force, which is balanced by the pressure of the balloon or the bubble in that case. Here's surface tension. This is a classic image. The molecules inside are attracted in all directions, including up, and the molecules at the surface are attracted in sideways and downwards, but no upward force is attracting them. And so the downward and sidewards force is slightly stronger because of the lack of surface. What other image should I prepare for you? Oh, there's a soap molecule or a film. This is the classic water trapped between soap, and that would be a thin soap film. And that would be the illustration for that. The sphere, an insect walking on the surface tension, and that would be that. Okay. How do I unshare my screen now?
Up the top, it will say stop sharing.
Oh, here we are. We're going to make that bigger, and this meeting is being transcribed. Okay, stop sharing. There we go. All right. Anything else?
I've got a couple of questions. I'm going to ask Bubble Dad, Chris, to unmute because I'm not sure I put your question in the right context.
Let me. Oh, can you hear me?
Yeah.
Okay. So when something dry hits the bubble, you were saying how the adhesion of the water molecules to whatever the dry object is, does that make that stronger than the water to water cohesion?
I don't have any research, and I looked measuring the difference in forces, so I can't say stronger. But the surface tension on a bubble versus a more significant material, I don't know the answer to that. However, there are some materials that the water is not attracted to, and so you can bounce a bubble off of some materials,
right?
Apparently steel wool. And so there's Tom and I have gone back and forth what exactly happens when you bounce a bubble. And, we're trying to speculate on things we can't see.
And when it's raining and you see, water droplets go through the bubble, that's easy to explain. When it starts raining harder, what's the force that's popping the bubbles at that point?
Oh, it's just physical impact. I mean, that's how you pop, how to pop a wall between two bubbles, yes?
Oh, right. Yeah. Mm-hmm.
Yeah, so you're just sucking real hard, so you're just hitting it. I mean, it's the same thing when you're blowing a bubble. You blow gently. Too much, you just blow it through it. Yeah. And we all do that because we have different wand sizes to accommodate different wind speeds. So that's just kinetic energy. Okay, there you go. All right, anything else I can help with?
I've got a Michelle has asked, yes, questions on color. I'm interested in what you tell the high schoolers.
When two waves interact, and I'm going to go ahead and go with waves, even though I don't like doing that, because light doesn't really travel as a wave. It travels as a particle, and it has to do with quantum probabilities and amplitude resolution of quantum probabilities, but it gets ugly. But up to high school, and certainly the first couple of years of college, they will teach them that light travels as a wave. And so you got a wave going up and another wave going up, and they add together. That's a characteristic of waves. So a +3 and a +3, now you have a wave that's +6. And with sound, that makes it louder, and with light, that makes it brighter. And if you had a +3 and a -3, they would actually cancel out. With sound, you would hear nothing. That's how noise canceling headphones work. And with light, you would see nothing. And so as the wave reflects, it reflects inverted. And as it travels through, it will bounce off the bottom and it will reflect. And if those waves are just perfectly aligned so that +3 and +3, that will be brighter. And in waves, light waves, the length of that wave depends on the color. The color is a function of wavelength. And so if the geometry is just right between the two things, that they come off so they're perfectly in step again, then it's brighter and we see that color. The other ones kind of get messed up with because they get interfered with +3 and -3, or +2 and -1. And so they're diminished and one is enhanced. And that's what constructive interference means. When the waves are, the term is in phase, but when they're locked in together so that the ups are going up and the downs are going down in the wave pattern, it's brighter. And that depends on how thick it is, at what points you will get a particular color being constructively interfered with. The rest of them are destructively interfered, so they're gone. And so that changes as the thickness changes, which particular set of waves will be constructively interfering. And there's some mathematics that have to do with odd number of half wavelengths, separating the differences. And you can tell what the thickness is based on what color is constructively interfered. It'd be a function of the wavelength. Does that answer that?
Yeah. Okay. Ian Russell, here's a question. Is our aim to make the audience feel that the bubble performer is clever, or to make the audience feel that they are clever?
Yeah, I know, Ian, we have had this conversation before. When I'm brought in to do a thing, I'm not a performer. I'm really out of focus here. I'm brought in as the science teacher. I start off being clever, and I want to get them to ask questions. Why would this happen? And a lot of the stuff I do has to do with that. What would cause that? How can this happen? And I do that with things I know the answer to, but I want them to kind of, and who thinks the cube is even possible? And so it's a balance between telling them what's happening, because there are some things they can't see, and there's some things they just can't. I tend to, when I'm teaching, I teach the history of how men came to these conclusions. And I'll say that people reach this conclusion because they saw this. Tomorrow I'm teaching a group of people that they're homeschooled, and I just discovered that they don't know about atoms. These are high school kids, and they don't know what an atom and a molecule is. So I'm going to teach them, I'll start with crystals. What could possibly cause these things to have this shape? And then what else am I going to do with them? Density. Why do things float and other things don't float? Figure that one out. And I've got a piece of pumice, which is a rock that floats, and a piece of ironwood, which is a wood that sinks. And then what's the third thing I'm going to do? And I'm going to pose it to them to try to figure out what's going on, and to see if they can. But I understand the performer isn't there to educate, they're there to stimulate their creativity. So we see that slightly differently because of our roles.
So Ian's follow-up to that is we just need to know when explanation is appropriate and when it's not.
Yes, and I start all of my, I started this whole conversation with, we don't have to know the science. We don't have to know any of it. But if you're going to talk about it, you need to know it, because I'm encountering a number of people who are explaining things incorrectly.
I'm
And
going to bring Ian in.
okay,
Um,
great, let's do it out, Ian. We've had this conversation before. Now, Ian creates a brilliant interactive equipment for museums where it's designed so by manipulating it, the kids can reach the conclusion without anybody telling them anything. Is that a fair assessment, Ian?
Yeah, Thomas, I've really enjoyed your presentation, and I've made assiduous notes. I especially loved the sequence that you were presenting the ideas in, and I'm going to use a lot of your ideas. That the point I was making really is that I just think that there's a risk for those of us who are not sort of so well versed in the science. I just think there's a risk of getting carried away and trying to look clever. I'm not talking about you, Thomas, I'm really not. But there's a risk of people latching onto this and trying to throw in a whole load of word salad into their presentations and confusing people, actually making mistakes without realizing they're making mistakes. You're taking risks once you move into this area, and you do have to get it right. And I actually think, I really do believe that in order to make the audience feel educationally empowered and cleverer than when they came in, just to help them make observations, thoughtful observations, think about what they're seeing. And the teachers will love this. It's the teachers, if you go into a school, it's the teacher's job, isn't it?
Yes.
To teach the science. It's what we're good at is getting people excited and getting them to see things and to enjoy noticing things. And the teachers will love this.
Yes, I agree. And as I said, and the reason I wrote my book was I was running into bubblers on the internet, and they were using science and using the vocabulary without really understanding what they were talking about. They heard somebody else say it. Oh yeah, surface tension. And what causes surface tension? Well, it's the air pressing down on it that makes it the surface. So that's why it has tension. And so, but I agree 100%. We don't need to talk about science, and we don't need to understand it ourselves. You know, I don't understand how my computer works. I don't understand, well, I understand a little bit about cars, but the new cars now, I can open the hood to change the oil. That's all I can do. But I can still use it. And I think the same thing is with the science of bubbles, is that you don't need bubbles. They're pretty. What causes them to have colors? And we had this discussion. Oh, they're like little rainbows. Well, no, rainbows, the colors are produced by refraction, and which is the bending of light. And this is caused by something completely different. And we came up with the analogy of butterflies. Butterflies produce colors by interference. And so instead of saying they're little rainbows, they're little butterflies, colorful butterflies. And so, yes, there's a danger of stepping in to the science without really understanding the science. And hence this conversation we're having today. But I appreciate that feedback, Ian. And gosh, if I gave you something to think about, I must have done a great job, because you're brilliant.
From Sebastian, thanks for the info, but I'll have to go. He's attached a link to a popular video made with the French National Scientific Research Centre, which covers a bit of everything that was said this evening. Thank you. Have a nice evening. And then a link, which the link will be in the description with the video as well, the recording. Also from Celine, thank you, Thomas. Very informative. I've got a question from Ashley. What difference does air temperature make And is that worth exploring in discussion with students?
Age level, no. Obviously, the temperature is the kinetic energy that the air molecules are traveling at. And at hotter temperatures are traveling faster. And so, as we discussed a few moments ago, sometimes kinetic energy can break bubbles, just blowing too hard. And so I don't know if, but it also makes the water evaporate much quicker. Yeah, that's a complex. There's vapor pressure that comes into play with temperature, and I don't think I would. I mean, you could say when it's hot, bubbles pop because the water evaporates, and so in that regard, I would use it as an excuse why something wasn't working, or preface. It's real hot in here. I don't know if these things are going to work because they're based on water, and when it's hot, water evaporates. So I could see mentioning temperature, but I certainly wouldn't incorporate it into a presentation unless it was important.
Question from Stephen. The study of soap bubble, what application has led, sorry, the study of soap bubble, what applications has this led to? Is science or society? Any example?
I almost copied the 3 paragraphs I was reading about all the different things that soap bubbles are in the bubble science has applications to, between manufacturing, transporting medication. There's just, but it wasn't my content, and I didn't do the research other than Wikipedia. So you'd have to go to Wikipedia. It's not something I've discovered for myself. But last night I was copying, some mathematics in case anybody wanted to know about the thickness of a bubble and stuff like that. But yeah, there's a lot of applications in industry, but I did not copy that information down.
Okay.
Sorry.
I've got a message from Becky. Are you there, Becky? If you'd like to unmute and ask your question, there you are. I found you.
Could you unfeature me so my face isn't constantly going in focus? And there you go.
I'm here.
I'm Becky.
Sorry, it took me a minute to unmute. I had a question about color. When I was making bubbles on the beach last week, my husband was photographing the bubbles and they were gorgeous. And several of the photos that we got in the morning sun, we noticed when he was going through the pictures that the bubbles were replicated in color on the sand.
The shadows of the bubbles.
The shadows of the bubbles, but they were colored.
Yes. Tom and I actually were doing an interesting research a couple of years ago where we were talking about the characteristics of the film as it affects colors. And I had a white laser and I shined the white laser at it, and some colors are reflected and other colors were transmitted through the film. And they were different colors. And some of the ones not part of the laser beam in the first place. And the shadows, and gosh, it's a number of years ago, CJ was talking about the shadows, the colors in the shadows. And so this led us into that exact thing that you're looking at. And it was a deep, deep rabbit hole. But the bubble can act as if it's reflecting red, then the colors that pass through will be missing some red. And if it's reflecting blue, then the colors that pass through is missing some blue. It's like the sky, is, well, that's not like the sky. All right, so at any rate, so yes, there are colors in the shadows. The light that passes through it is different and spectacular. Some really beautiful ones. And the other point is that the color of the bubble depends on the light you're hitting it with. There's certain characteristics of lights that some lighting is better than others for bubble colors. The people that use LEDs for their bubble domes, I don't understand. White light has all the colors you ever want. Why would you put blue? I mean, I get that it's fancy and you put some smoke, you do some stuff with it, but I don't get it. I understand it, but I just, you got white light. Why would you want anything else? It's like, people want blue bubbles. Wait, the bubble's fascinating. Why would you want put dye in it, so now it's blue. And so, but yes, the light itself has something to do with the color of the bubble, and your shadows, the things you were seeing, had to do with the fact that some of the colors were being filtered out. Yes,
Yeah, I
no?
just never seen shadows with color before.
Yeah, they're spectacular.
My other question was something that I heard at convention. I mean, at the Bubble.
Bubble Fest.
Yeah, Bubble Fest. Thank you. And Tom Noddy referred to the thickness of a bubble being the same as, and I cannot find where I wrote it down, and I can't remember what he said.
All right, here you go.
Shall I bring Tom on that?
No, I've got it.
Okay.
The thickness of a soap bubble can range from 10 nanometers to 1,000 nanometers, whatever a nanometer is. A wavelength of light, and I think one of the things he mentioned is that a soap bubble is thinner than a wavelength of light. A red laser light has got a wavelength, the distance from one wave to the next, of about 650 nanometers. And so a bubble at 300 nanometers is half the thicknesses of a wavelength of light, which I believe was the thing that he mentioned. Vastly smaller than a human hair. And I believe a spider silk is 3,000 nanometers. And so we're talking about real small distances. And incidentally, that black film that you see on a bubble, the stage just before that, sometimes called the gray film, the thinnest thing that you can see with the human eye, soap films. And it's downwards of 30 or 40 nanometers, whatever these nanometer things are. At a certain point, they just lose meaning, except to compare other things to them. And I don't even know what a human hair is. It's 20 times bigger than spider silk. So it'd be,
Okay, thank you.
Anyway, there you go.
So Ian Russell's mentioned typical bubble thickness can be close to the size of a bacterium. Bubble Dad, I once read 1/10,000th as thick as a human hair. 10,000? Yeah, 10,000.
Yeah, that's all right.
So Caroline and Cheryl, what is the best way to describe how thick a bubble is? I think we just done that one.
Yeah, I don't know, Ian. I don't know. I mean, compare it to a human hair. I like the spider silk. 100 times thinner than spider silk.
Okay.
That would be so times 30 would be 3,000. Yeah, that would do it.
Oh, she's done it. How do you describe that foam looks white?
It disperses light. The light's getting dispersed all over the place, and if the light source is white, then then what we see is white. If you shine a blue laser at the foam, it'll look blue. It's why the egg white. You take an egg, which is runny yellowy thing, and you whip it up enough, you put enough air in there, it looks white, because now the light's getting in, it's being dispersed everywhere in all directions, and it lights up white. It's kind of like why the sky is blue. Light hits the sky, the blue wavelengths get scattered. It's something called Rayleigh scattering. And so it scatters the blue lights throughout the sky. So you look off away from the sun, and the sky appears blue because the light's bouncing around and some of it gets to your eye. If you did that on the moon, where there's no atmosphere, you would just see this light from the sun, and you wouldn't see the atmosphere because there's nothing there to reflect the light.
Okay. Michelle, at Bubble Fest outdoors, it seemed that the bubbles Aramis made were a little different color, maybe tint or intensity than everyone else's. Your thoughts?
Is Aramis here?
No.
Okay, he gave me his formula, and I've tried making it unsuccessfully. I think one of the odd ingredients he had, I got the wrong version of it. but Aramis's formula has some interesting things in it. And obviously the color of the bubble is a function of how it interacts with light, and how it interacts with light will determine on the materials. But I don't know. I can't. I've got his formula, but I don't know. I haven't been able to get it to work yet, so I haven't tried it for myself. And at Bubble Fest, I was busy because I had the only station that kids could make their own bubbles, and I was busy all day. Well, you guys were off together making bubbles together. I was keeping kids from running off with my wands. So, fun and games.
Spider silk is 3,500 nanometers according to Google, approximately 10 times a bubble thickness. Thank you, Ian.
Well, that's a bubble thickness at 300 nanometers. So now you can get down to 10 to 50 nanometers, and so you're cutting that by a fraction. But yeah, but exactly. If you're going to talk about the bubble thickness, you do it by comparing it to things that kids are familiar with.
Like paper.
Yeah. Anything else?
Any other questions?
All right, my work here is done. Buy a copy of my book. Oh, did you notice the real nice wands I used? Aren't they amazing? Gosh, you could get a set of these wands and get the best tools. No, that's it.
Well, I'm sure I speak for everybody here when I say thank you to Thomas for this incredible talk. It's been extremely enlightening. I've learned quite a lot, and I'm sure many of those attending the talk, and indeed those watching at a later date, will learn quite a bit as well. If you do want a copy of Thomas's book, it's still available on Amazon. And if you want some of the tools that he was demonstrating with, you can reach out to Thomas as he sells those as well as other incredible bits of kit like the double bubble wand and the tilt-a-whirl. Ask him about those, they're great. So from AOIBA, who very kindly sponsored this talk, thank you, and we hope to see you at some of the other talks in the future. Take care. Bye-bye.